My name is B. Ravindar, Assistant Professor in the Department of Electrical Electronic Engineering, BVR at Sapur. And today I am discussing about on Power System 2 in the topic of fault analysis. So in this short circuit fault analysis, we have to study on this line to ground fault analysis, LG fault, and double line fault, line to line fault. Then we can go for about double line to ground fault, and these faults are called unbalanced or unsymmetrical faults, and this line to ground fault is mostly occurred, that is 70% of the fault we can observe in transmission lines or distribution systems, mostly LG faults. Then double line fault is 15%, double line to ground fault is occurs 10%. Next is triple L faults, line to fault, line to line to fault, and fifth one is line to ground fault, triple LG fault. So these faults are called balanced fault. Triple L fault or triple LG fault are called balanced fault, and it is mostly 5% of this fault is occurred in these three-phase faults. And the various fault in order to increasing of severity. So which fault is most severe and which fault is frequently occurs. So LG fault is most frequently occurs in case of our systems. We can see in electrical system mostly LG fault. LG fault means when three faults and one line may break. So this one is more frequently it is occurred. And next is frequently double L fault, then double LG fault. So double L fault means two lines can be touched. R phase and Y phase both can be touched due to this wind or maybe some the rain effect. It may be having the two lines may be touched. Then triple LG fault is most less frequent occur. So triple L or triple LG, three line RYB phase short circuit means very less frequency of occurrence will be there. That may be due to that maybe some monkeys will be fall on these three lines, or maybe some snakes will come. So but it is mostly less pronounced. And severity of the fault, which fault is more severe? We can see the more severe is triple L fault. So if the three lines gets short circuited, there is more current can flow, and that fault is more severe. And less severe fault is LG fault. So line to ground fault is less severe fault. So in the objective exam, he may ask you that which fault is most severe fault, triple L fault or LG fault, double L fault, like that. So triple L faults. And which fault is more occurrence in case of the system, in this fault analysis, we can see that LG fault. So like that he may ask in the objective exams. And next one is unsymmetrical fault analysis. For that unsymmetrical fault analysis, we can see that VA0, VA1 means these are the voltage in terms of this current. We can see that what relation this unsymmetrical component voltage are current into a symmetrical voltage or current. So this VA0, VA1, VA2, this one is zero sequence component, positive and negative sequence component in this voltage. We can see minus Z0 into IA0, and this VA1 means EA minus Z1 into IA1, VA2 means it is minus Z2 into IA2. Then VAVB, we know that in case of this unbalanced quantities, VAVB, that we are representing as A, 1, 1, 1, 1 A square A, 1 A square, VA0, VA1, VA2. And this current relations IA, IB, IC, 1, 1, 1, 1 A square A, 1 A square, 1 A0, A1, A2A. So these are the unbalanced quantity, and it is a symmetrical represented voltage and current. And symmetrical component voltage or current into a unsymmetrical voltage or current. So that we are writing just taking as this VA0, VA1, VA2, and this one is A, so it is A inverse. So that A inverse is nothing but 1 by 3, 1, 1, 1, 1 A square, 1 A square A, VA, VB, VC. Similarly for the current also, IA0, IA1, IA2, that is a symmetrical component, and 1 by 3, 1, 1, 1, 1 A square, 1 A square A, and IA, IB, IC, these are the unbalanced quantities. So in next we can see that fault analysis, LG fault. So how we can analyze the LG fault in the system? If there is a LG fault, so what is the analysis is there? So without fault impedance, now we are considering that this fault is occurred, and that fault line it is not having any impedance. That case we are saying consider a three-phase system with a earth neutral and alternator is unloaded. So we are considering that the alternator is not having any load condition. So let a single line to ground fault occur on the phase A. So one particular alternator, if there is a fault is occurred at this alternator at phase A. So we are considering the phase ABC, but in practical it is RYB. So A phase there is a fault occur, and this fault, if a fault is occurred on phase A, only one phase, then we are calling as it is a single line to ground fault, one line to ground. So LG fault is occurred, and this particular alternator is connected to neutral. So the boundary condition, for this case you can see that this alternator is not connected to any load. So this IBIC, so VA equal to 0. If the fault is occurred, if a short circuit occur, we know that if there is a short circuit, then voltage will be 0. If the open circuit, like this open circuit is there, then the current, this voltage will be infinity and current is 0. Here V is 0, but current is high current, not only infinite, but it is high current can be flow if it is short circuited. So this VB, you can see that VB and VC are open circuited. So VB is not equal to 0, it is having some voltage, and VC also not equal to 0, and IA is not equal to 0, it is having high current, and IB is 0 because it is an open circuit. IB, IC are open circuit. So IB is 0, IC equal to 0. So these are called boundary condition. When the fault is occurred at phase A, VA equal to 0 and VB, VC, these phases are not equal to 0, VB, VC are not equal to 0, but currents are 0 because open circuit. And the fault current is now, this is the fault current. The fault current is flowing from A phase. The fault is occurred at A phase and the fault current is flowing in A phase. So this, how we can get this LG fault. So IA0, IA1, IA2 are the symmetrical quantities, and 1 by 3, 1, 1, 1, 1 A square, 1 A square A. That we are writing these boundary condition values, since IB equal to 0 and IC equal to 0. Now we can write this IB and IC is 0. Now we can realize that IA1, IA0 equal to nothing but 1 by 3, 1 into IA. So you can see that IA0 equal to, and IA1 also you can get. So IA0 equal to IA1 equal to IA2 equal to this IA by 3. IA by 3 means all these positive sequence, negative sequence, zero sequence component value is nothing but IA by 3. All these currents are equal. Same current will flow during this LG fault. And substitute this equation 1, then we can get this in your equation 1. So in this relation, if you substitute in the voltage relation equations, what we are having in the first. So this is the voltage equation we are having, VA0, VA1, VA2 equal to, in this relation if you substitute, so then we can get, then in the voltage relation if you substitute, then VA0, VA1, VA2 and this IA1, IA0, IA1 and IA2, all currents are, we are, if you are taking any one term, that is we are representing in terms of positive sequence, IA1, IA1, IA1. Now we can write that VA0 equal to nothing but minus Z0 into IA1, and this VA1 is nothing but EA minus Z1 into IA1. So if you multiply this Z1 into IA, and this VA2 is nothing but EA, this VA2 is 0 now. So 0 minus Z2 into IA1. Here it is VA0 is nothing but 0 minus Z0 into IA1. So it is minus 0 means it is 0 minus IA1 into Z0. VA1 is nothing but EA minus Z1 into IA1. VA2 is nothing but 0 minus Z2 into IA1. Then we can get minus IA1 into Z2. So like that we are getting the symmetrical voltage equations. So we can consider equation 2. So from this sequence component, we know that VA equal to VA0 plus VA1 plus VA2. So and VB0 and VC0 plus VC1 plus VC2 is nothing but VC. And VA equal to what we are getting in the fault, in this LG fault, VA equal to nothing but 0. VA equal to what is nothing? VA0 plus VA1 plus VA2. So this sum of this sequence voltages are equal to 0. Then we are getting that this relation from equation 2, VA0 plus VA1 plus VA2 equal to 0. You have to add all these three voltage sequence voltages. Then we are getting as VA0 means minus IA1 into Z0 plus VA1 means E0 EA minus IA1 into Z1. VA2 means minus IA1 into Z2 equal to 0. And then you can see that from this relation Ia1, if you take common, then Ea will comes like this. It is minus Ia1 into Z0 minus Ia1 Z1 minus Ia2 into Z2 equal to Ea. So from this equal to minus Ea. Okay, so it is minus Ea, minus if you take common, then it will be cancelled out. Then so Ia1, if you take common, it is Z0 plus Z1 plus Z2 equal to Ea. Then it is Ia1 equal to nothing but Ea by Z1 plus Z2 plus Z0. So you can calculate the this Ia1 sequence component, you can calculate. And we are observing the from this LG fault, Ia0 equal to Ia1 equal to Ia2, means all currents are equal. So means these three sequence currents are equal. So we need to add this sequence component. So already we seen that last class we seen that symmetrical component, this particular alternator, we have the three components. One is positive sequence, negative sequence, zero sequence component. For an alternator, we need to represent positive sequence, negative sequence, zero sequence during the fault. And that positive sequence component is means the voltage source in series with the impedance, and this negative sequence component is only having one impedance, and this negative sequence is also having single impedance. And these three networks means these three circuits we need to connect in a series. The positive sequence, negative sequence, zero sequence, three we need to connect into series. So this one is say Ea and Z1. This is the Z1. This one is positive sequence, and this one is negative sequence. This one is zero sequence. So all these three, so these three elements now we are connected in series. So you can see that these three circuits, the positive sequence, negative sequence, are connected in series. Why we are connecting series means during the LG fault, Ia value Ia0, Ia1, Ia2 equal to Ia by 3. So all these currents are equal. Equal current means during series. So we are connecting in series. Then we can calculate the Ia0 or Ia1. So the fault current is given by the fault current. You know the formula is If is nothing but Ia. The fault current is nothing but If equal to Ia, and that value is nothing but 3 times of Ea by Z1 plus Z2 plus Z0. We are getting that Ia1 equal to Ea by what we are getting Ia0, Ia1, Ia2 equal to Ia by 3, right? From this Ia equal to nothing but 3 times of Ia0 or 3 times of Ia1 or 3 times of Ia2. So Ia is the fault current. So Ia equal to nothing but 3 times of Ia1. So 3 into Ia1 equal to how much? Ea by Z1 plus Z2 plus Z0. So 3 into Ea divided by Z1 plus Z2 plus Z0, it is your fault current. So first we need to calculate the sequence component of current, that is your Ia1 or Ia0, any value, and multiply with the 3, then we can get the fault current. Okay, so these fault currents, so this Ea value, if it is in a per unit values, then we need to take this fault current is in per unit. Okay, and if you want to get the if you want this actual value, then this per unit value into actual value we need to multiply. So during the problematic, we need to calculate the what is the fault current. That fault current we need to analyze for the circuit breaker ratings. So from this observation, we can see in case of LG fault, the neutral of the generator is not grounded, zero sequence network is open circuit, and Z0 is infinite. So suppose if this LG fault is occurred, so we are having this alternator, we are representing like this, and if it is not grounded, solidly it is not having any ground connection. So this is not grounded, then this Z0 is having infinity. Okay, so Z0 is infinity, and if there is a fault is occurred, there is no path of current flow from this fault point to this neutral point. Then Z0 is infinity. Then what we are having this fault current If is nothing but 3 times of Ia0, that is 3 times of Ea divided by Z0 plus Z1 plus Z2. Z0 is infinity. Infinity means 1 by infinity means you can get 0. If equal to 0 current. So if it is not having any ground connection for a LG fault, there is no fault current cannot flow. Second point, you can observe that from this equation, IA1 is 0 when Z0 is infinity and IA1, IA2 must be 0. Then IA also gets 0. And second, we can see the same result can be seen use of symmetrical components, since the circuit does not have any path of flow of current in the fault unless there is a ground at the generator neutral. If you are not connecting any ground at this point, so we can't get the LG fault current. So in order to get LG fault, the alternator should be connected to the ground. Next is with fault impedance. So with fault impedance, how we can calculate? So previous derivation is without fault impedance. Now we can see that with fault impedance. Let us assume as LG fault occurs on the phase A, as shown in here, we can see that LG fault with fault impedance. So there is having a fault impedance. If the fault is occurred at this A phase with a fault impedance of ZF, then you can see that how this equation can be varied. The boundary condition for this is VA equal to, in previous VA equal to what? 0. Now it is VA equal to IA into ZF. It is not 0, it is VA equal to IA into ZF. So if you take this plus minus current is entering, then it is IA into ZF is nothing but this VA current. Across this, if you take loop analysis, we can get this VA equal to IA into ZF. And IB and IC are open circuited, it is 0. It is not, this alternator is not connected to the load. And the fault current is now, it is IF equal to IA. So everything will be same, only the VA equal to 0 is the relation get changed. Then we can see the fault current, anyhow it is having IF equal to IA equal to IA naught plus IA naught 3 times of IA1. Okay, 3 times of IA1. And IF equal to 3 times of IA1, IF equal to IA equal to 3 times of IA1, that is 3 times of EA divided by, the same relation will be there, Z0 plus Z1 plus Z2 plus 3 times of ZF. We can get as, we need to add 3 times of ZF in this case. So this sequence network of these equations are given as VA0 equal to minus IA0 Z0, VA1 is EA into EA minus IA1 into Z1, and VA2 is nothing but minus IA2 into Z2. The same thing, the current will be same, the sequence whatever it is there. So all are connected in series, but only 3 times of ZF gets added. So the current which is flowing here, it is 3 times of IA0. This IA1 current is 3 times of IA1 is current is flowing here, and we can calculate it as IA equal to IA0 equal to IA1 equal to IA2 equal to 3 IA, 3 times of IA. So that is 3 times of IA by 3. Sorry. IA by 3 equal to 3 times of IA0, IA1, IA2. From this, IA equal to nothing but 3 times of IA0 equal to 3 times of IA1. Here we are getting all are in series sequence. Then it is not a ZF, it is 3 times of ZF we need to take here. So here the current is IA0 equal to IA1 equal to IA2, and these currents are 3 times of ZF into IA0 we need to add it in case of with fault impedance. Next is double line to ground, double L fault. So next to fault analysis we need to analyze is line to line fault, what is known as line to line fault. So without fault impedance, how we can calculate it? So without fault impedance, let us assume that double L fault occurs on the phase B and C. So there is a fault is occurred at phase B and C. So the fault is occurred at the phase B and C. So at B phase and C phase, the double L fault is occurred. Now we can see that IA is open circuited. Now we can write the boundary conditions are, this VA is not equal to 0, VA is, and VB and VC are equal to VC. So VA is not equal to 0 because it is a open circuit. IA gets 0. So IA gets 0 and IB plus IC. So these two currents are added. Okay, if you write a KCL here, two current are entering. So IB plus IC equal to 0. Entry current equal to leaving current. Leaving current is not there. So IB plus IC equal to 0. Then this IB is nothing but minus IC. So we need to write in case of symmetrical analysis, this IA, IB, IC. There we need to write IB in place of IC in place of minus IB or any one relation we need to write. So symmetrical component voltages are given. This VA naught, VA1, VA2 equal to 1 by 3, 1, 1, 1, 1 A square, 1 A square A, and this is VA, VB, VC. VA is not equal to 0 and VB, VC are 0. So we can see that VB equal to 0 and VC gets 0. So if you can substitute, so then VA naught equal to nothing but 1 by 3. So 1 into VA, VA. So it is VA plus VB plus VC like this. So it is first we are writing these relations. So we get from this relation 1 by 3 VA, VB, VA, VB. This one is again VB, we are writing as VB equal to VC. So this voltage, both voltages are equal because at same point these are connected, then VB equal to VC. In terms of voltage relations we are writing, not in current, and first we are writing in voltage relation. Then it is VB and VB. Then it is VA naught equal to 1 by 3 into VA plus VB plus VB. Same 1 by 3 A VB, A square times VB. And VA2 is nothing but this negative sequence. It is 1 by 3 into 1 into VA, VA plus A square into VB, A into VB. Then we can get this relation. Then finally, this we can observe these two relation VA1 equal to VA2. VA1 equal to VA2 means this positive sequence and negative sequence voltages are equal. Positive sequence, negative sequence voltage are equal means both this positive negative sequence networks are connected in parallel. So this symmetrical components currents are given. So we seen that IA equal to 0 and IB equal to minus IC. So IB equal to minus IC we are writing and this IC again IC only. Now we can write the relation for this. IA naught equal to 1 by 3, 1 into 0, 0, 1 into minus IC, minus IC, 1 into plus IC. Then it is get as minus IC plus IC. So IA naught equal to gets 0. And IA1 equal to, we can derive from this 1 by 3, 1 into 0, 0, A into minus IC, minus A into IC, A square plus A square into IC. It is your IA1. Okay. And IA2 is nothing but 1 by 3, 1 into 0, 0, A square into minus. It is minus A square into IC, A into IC plus A into IC. So you can see that if you take a minus here, it is minus A square plus A square. So any one relation, it is minus times of, it is we can write as minus times of IA2, 1. So from this we can observe that IA2 equal to nothing but minus IA1. So IA2 equal to minus IA1. So equation 2 with a connection from the generator to neutral ground, Z0 is finite and so that VA0 equal to 0 and IA0 is 0. And substitute in the equation 1, then we can write as the equation we can see that. So equation 1 in this VA1 and VA2 relation if you substitute in first equation it is in that VA0, VA1, VA2 in this relation if you substitute it is 0, EA0 minus Z0 0 0 0 Z1 0 0 0 Z2 into IA0, IA1, IA2. In this relation if you substitute, so VA0 equal to 0, this one is 0 and VA1 equal to VA2. So this one we are writing as VA1 equal to VA2 and this IA0 we are getting as 0, this one is 0 and IA1 equal to same and IA2 is equal to we are writing as minus IA1. So now we can multiply this. So it is 0 and VA1 equal to EA minus Z0 into IA1. So we can get as VA1 equal to nothing but this 0, this VA0 we are getting as minus IA1 Z1, VA1 equal to this one, VA2 is this one. Then we are getting this relation from this VA1 equal to this one we can get as 0. This VA0 is 0. This is 0 and VA2 is 0. It is minus, instead it is VA1 equal to minus into minus plus IA1 into Z2. This one is this value and here it is actually 0 it is. Then EA equal, from this equation 2, you can see that VA1 equal EA minus IA1 into Z1 equal to VA1. VA1 equal nothing but VA2. What we have the relation as VA1 equal to VA2. So from this relation, VA1 equal to VA2. So we have the relation of that VA1 equal to VA2. So then VA1 equal to VA2 if you substitute, VA1 equal to VA2 if you substitute, then IA1 equal to this VA1 E minus IA1 into Z1 equal to, this is the VA1 and that is equal to VA2, that is equal to IA1 into Z2. So if you equate these two, then you can get IA1 equal to nothing but EA E minus EM equal to EA equal to IA1 Z1 plus IA1 Z2. So you can see that IA1 take the common, then it is IA1 equal to EA into by Z1 plus Z2. Then you can get this relation. So that IA1 equal to nothing but EA by Z1 plus Z2, you can get it. And we know that in the relation as, so this IA, IB, IC, the unbalanced quantities 1, 1, 1, 1 A square A, 1 A square. And here we are getting this, this value of IA value is, IA naught is 0. This is 0, IA1 and it is IB and this IA1 minus IA1. Then if you multiply these two, so we can see the relation as IA equal to 1 into 0, 0, 1 into this IA value. We can write as IA equal to IA1, 1 into this minus IA1. IA1 minus IA1 means it is 0. IB equal to, we can get as IB equal to 1 into 0, 0, A square into IA1, A minus A into IA1. So it is A square minus A into IA1. Then we can get further relation as this A square minus A is nothing but it is minus J root 3 into IA1. So A square minus A, if you take these values, we can get as minus J root 3. So otherwise we can see that A square minus A means, A square means it is 1 at an angle 240 minus 1 at an angle 120. If you do this one, it is minus 0.5 plus minus J 0.866 and it is minus minus plus 0.5. This one is, we can get as plus J 0.866. Then it is, these two cancel, 0.8, 0.8. Then you can get 1.73 something. So it is nothing but minus J root 3 into IA1. So this value you can get as IB value. The fault current is given by, we know that fault current, it is occurred in B phase, then IF equal to IB, that is for minus J root 3 into IA1, and we know that IA1 is nothing but EA divided by Z1 plus Z2. If you substitute that, then it is your fault current. So fault current relation in case of a double line fault is minus J root 3 EA divided by Z1 plus Z2. So this sequence network equations are given. So VA1 equal to VA2 means positive sequence, negative sequence voltages are equal. That is EA equal to minus IA1 Z1 equal to minus IA2 times Z2. From this we can get as EA value. Means we can see that it is your positive sequence network. It is a positive sequence network. It is a positive sequence network, and zero sequence network is this one. And these two networks are having same voltage. Same voltage means these are connected in parallel. So then we need to connect as parallel. This negative sequence and positive sequence networks are connected in parallel. And there is no zero sequence in this case. Zero sequence is absence. Because there is no zero sequence because it is not having any involvement of ground connection. So next, from this observation, we can see for this double L fault, there is no ground at the fault, so no current can flow into the ground. So there is only B phase and C phase get faulted, so there is no ground involvement. So in this derivation, IA naught is 0, so hence 3 times of IA naught is neutral current also gets 0. And the presence of this or absence of this ground neutral at the generator does not affect the fault current. either a neutral may exist or may not exist. It does not affect on the fault current. And if the generator neutral is not grounded, Z0 is infinite and VA0 is indeterminate, but the line to line voltage may be found since they contain no zero sequence component. And with fault impedance, now double L fault with fault impedance. Let us assume that double L fault is occurred on phase B and C and shown here with a fault impedance. Now we are having fault impedance. So from this observation you can see that it is VB and VC, it is a plus minus, it is VC and it is VB, and if you take the loop analysis of this one, if you see that minus VC minus ZF into IB and it is plus VB equal to 0. From this VB equal to nothing but VC plus IB into ZF. So it is the, if you take the loop analysis, we can get this relation. So VB equal to VC plus IB into ZF. In previous case, we are saying that VB equal to VC. Now it is plus IB into ZF. And IA is open circuited, IA is 0 and IB plus IC. Both currents will be flowing in the same element. So it is IB plus IC is 0 and IB equal to minus IC. So only thing is here I added the element. The fault current is given in this case, the same fault current IB equal to minus J root 3 EA by Z1 plus Z2, and the sequence network equations are given, this VA1 minus VA2 equal to IA1 into ZF. So these two voltages, in the previous case VA1 equal to VA2 with fault impedance means VA1 minus VA2 equal to IA1 into ZF, and EA equal to EA minus this fault impedances. If you write the relations, so VA1 means EA minus IA1 into Z1, this VA2 means minus IA2 into Z2, minus into minus plus equal to IA1 into ZF. From this networks, we can see these two voltages are this voltage VA1 and VA2, so it is plus minus, and if you take loop analysis and it is IA1, so it is same VA1 minus VA1 minus this IA1 into ZF plus VA2 equal to 0. This relation it need to satisfy. Then the ZF is connected between these two positive networks and network. It is a positive network, positive sequence network, and it is negative sequence network. Both are connected in parallel with the impedance ZF. From this you can see that equivalent circuit of this generator during double L fault with fault impedance. We are including the fault impedance. So next class we can discuss about on double line fault, and then we can see about on triple L fault and some problems. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.